Hello students, welcome to my next lecture on the PY question series. Today we will discuss about bounded variation. Myself Dr. Harish Garg. I will cover all those questions from the 2011 to 2023 from CSIR NET examination. You can simply follow my YouTube channel where you can find the playlist of the CSIR NET, UGC and IIT JAM. Here you can find the topic wise PY questions of the different topics, real, complex as well as the statistics analysis. You can see some question on the GATE as well as the CSIR NET examination. All are available in the shortcut tricks. Also you can see the PY questions related to testing of the hypothesis and the statistics portion as well. So let's start with this. What is the objective of this lecture? We will cover all those questions related to the bounded variations from the CSIR NET as well as NVHM examinations. We will cover the 45 plus questions related to the part B and part C. And definitely we will cover all those questions with the help of shortcut tricks. So what is the objective of that? The objective is, firstly we will try to examine which of the following functions is my bounded variations, or you can say any of the combination of this, like x square plus 2 plus of greatest integer, or you can say x plus root x plus sine of x, and many more are there. How you can examine whether they are bounded variation or not. Some more examples are there like logarithm, sine, cosine, or more functions like of these cases are there. So our objective is we can examine whether they are the bounded variations or not. How we can examine? I will tell you the various shortcut tricks firstly for these cases, and then we will cover on this CSIR as well as NVHM examinations. So listen very carefully about this various shortcut trick. The first shortcut trick: any of the function f from the x to y is set to the bounded variation if this f is my bounded and monotonic. If this f is my bounded and monotonic, then the function is said to be the bounded variation. Second rule is, if you prove that the derivative of the f is existence for all x and it is a bounded, that means if it is a mod of f dash is less than of the k, or you can say if f satisfy the Lipschitz condition, this is nothing but my Lipschitz condition, then this implies function is my bounded variation. Remember, in the both of the cases, converse need not be true. Converse not always true. Fine. So whenever you want to prove is a bounded variation, you have to check whether it's a bounded and monotonic both, or if it is satisfy the Lipschitz condition, then the function is bounded variation. On the other hand, remember this boundedness is only the sufficient condition, not necessary. Another, if you prove that the function is a bounded variation, it implies function is bounded. Also, converse need not always true, or you can say if the function is not bounded, what is the opposite of this? If the function is not bounded, it implies it is not bounded variation. So if you want to prove that the function is not bounded variation, you prove that the function is not bounded. How you can prove that the function is not bounded variation? First of all, you have to check whether the domain is bounded or unbounded. If my domain is unbounded, like of this, then the function is not bounded variation. Second is, if you prove that the function is unbounded, then the function is again not bounded variation. So based on, firstly, this is my first tips for you. So based on this, I will check about here. You can see that domain is my unbounded because infinity involved. So it means it is not bounded variation. Look at this one. Again, because of this infinity, the domain is my unbounded. So if the domain is unbounded, the function is not unbounded as I mentioned here. You can see that domain is my bounded. Fine. But remember, as I told you, bounded does not imply the bounded variation. But look at that. This function will go to the infinity as x approaches 0. It means function is my unbounded. So if the function is unbounded, it means this is my not bounded variation by using this shortcut tricks. Look at this another one. This is my bounded. Fine. and on the 1 and 3 it is my 1 over 9 to 1, which is again a bounded. Fine. So you can't discard them. Remember, these tips are used to discard the option. So this we can't say anything right now. We will see in the later on whether it's a bounded or not. The function is bounded, domain is bounded, but we can't say it is a bounded variation. It is a bounded, function is also bounded over this, so we can't say anything. Greatest integer, you can see that it is a bounded. On this interval it is also bounded, so we can't say anything. R, what is the R is? Minus infinity to plus infinity. So on this it is my unbounded. Once this is my unbounded, what does it mean? It means this is my not bounded variation. Again you can see this is my unbounded. So interval is unbounded, so this is again not bounded variation. So right now we are unable to justify this, we are unable to justify this, and we are unable to justify this. Fine. These are first shortcut tips for you. Now look at this one. The function is my bounded, but again when x is 0, this function will goes to the infinity, so it is not unbounded, it is not bounded variation. It is a bounded, on this it is also the bounded, so this is a bounded, this is bounded, so we can't say anything. And these are the sine and cosines. We will discuss sine and cosine later on, because this is a bounded, this is bounded, all are bounded, and this is also bounded in this domain. So we can't say, we can't discard the bounded variation. Look at this one. This is a bounded function, this is a bounded domain, this is the bounded, this is bounded. You can see the function is less than 1, so it is a bounded. It lies between 5 and 10, it's a bounded. It is again a bounded, it is again a bounded. So we can't discard any of the option. Now look at the second tips for you. Whenever you are working on the sine and cosine terms, fine, that is any of the function is the form of the x raised to power a sine c x raised to power b, or you can replace by the cos, like of this. You can see here, you can see here. So this function is said to be bounded variation if and only if whenever this a is strictly greater than of the b, and c can be any number but it's a non-zero. F is said to be the bounded variation if and only if a is greater than of the b, strictly greater than b, and c is a non-zero. And the function is said to be the not bounded variation if a is less than or equal to b. Fine. Now you can see about here. This. What is the a? A is my 1, b is my 1. So clearly say 1 is not greater than 1. So it is not bounded variation. Here 2 is greater than 1. So yes, this is a bounded variation. This is the 1. So a is my 1, b is my half. You can see c is my non-zero. So a is greater than of the b. So yes, this is a bounded variation. 4 is greater than of the 2. Yes, this is a bounded variation. We already proved that this because 0 is a bounded, but when x is 0 it goes to the infinity. So this is not bounded variation. This is the bounded, this is the bounded, so we can't say right now based on still tips on here. Fine. So this is the second tips which is very useful for you, how you can check whether the function is bounded variation when it involves the sine and cosine terms. Look at the next tips for you. Till now you can simply scan and join my WhatsApp group if you want to join with me through my WhatsApp group. Another tips for you. These are third tips for you. If you have the two bounded variation function, if f and g are the two bounded variation, then f plus g and f minus g both are my bounded variation. However, the product is a bounded variation only if f and g are my bounded. Remember here there is no condition for that, but in this case you must have a bounded this one. Always remember, bounded variation implies it is a bounded, but converse is not true. I said f and g are bounded, it doesn't mean that f and g are bounded variation. If f is my bounded variation, then the reciprocal of this may or may not be a bounded variation. However, if you prove that the absolute value of this fx is greater than or equal to something where k is my constant, then you can say 1 over f is my bounded variation. Look at this examples. You can see it is nothing but f minus g, that is a fractional part, that is a fractional component. So if I say x minus mod of x, so clearly say domain is my bounded. Fine. You can see if I consider f is my x, domain is my 0 to 50. Now clearly says this function is my bounded over this, plus this function is my monotonically increasing. Fine. If the function is bounded, if the function is monotonic, it means this function is my bounded variation. Fine. So this is my bounded variation. Clearly says more greatest integer of x over this domain is my bounded. Also greatest integer is my monotonic. It is not a continuous function, but it is a monotonic function. You can see the graph of this is my here, it is a monotonic. Once the bounded plus monotonic, it means it is my bounded variation. So this is also the bounded variation. So if I consider this is f, this is g, the difference of them is also bounded variation. So yes, this is my bounded variation. Look at this one. Again x cube over this is my bounded plus monotonic, because x cube is a monotonic function. So it's a bounded variation. Sin x is a bounded function over the 0 and 1. Sin x is a monotonic function over the 0, 1. So yes, this is also the bounded variation. Difference of them is also the bounded variation. Moreover, you can also see if I consider f is my sin x. Fine. So clearly says that derivative of this is less than of the 1. It means, and what is the derivative is my cos x. This is existence for all x. F dash is less than 1. It means it satisfied Lipschitz condition. It means this f is my bounded variation. Either you can prove by the Lipschitz condition, or you can say it's a bounded plus monotonic. Again, sin x satisfied my Lipschitz condition, or over this domain is a monotonic as well as bounded. So it's a bounded variation. Root of x over the domain 0, 1. It is a bounded plus it is also the monotonic function. Fine. Either of the monotonic is a monotonic increasing or a monotonic decreasing. So you can see root of x is a monotonic increasing function. So therefore it's a bounded, it's a monotonic. So therefore this is also the bounded variation. Sum of them is a bounded variation. Yes, it is also bounded variation. Look at the last part. If I consider the last part is a fraction. First of all, you can see whether 1 over f, can you say x minus 2 is greater than of something for all x in this domain? Yes, you can see it is always be greater than of the 1 or greater than or equal to 1. So this is a non-zero k. So it means this also, this is my bounded domain. On the 3, infinity, this is my finite. On the 3, 8, this is my finite. Fine. This is my bounded. This is my monotonic. So this is my bounded variation. Tan x on the interval 3, 8 is a bounded. It is a monotonic. So it means this is a bounded variation. So this is the bounded variation. This is the bounded variation. Sum of them is also the bounded variation. Hence, this is the bounded variation. This is the bounded variation. This is the bounded. This is the bounded variation. So all are my bounded variations. Okay, look at this one. If f and g are the monotonic functions, then f minus g is also the monotonic. Look at this same one. You can see x is my monotonically increasing function. Greatest integer, it is also the monotonic increasing function over this domain. So both are my monotonically increasing. So therefore difference of them is my bounded variation. This is the first way. I already explained you, if you prove this is the bounded variation, this is the bounded variation, that sum and the difference is also the bounded variation. Again you can see this one, sin x is my increasing function, monotonic increasing function, because derivative is my cos x. On the x of 0, 1 is always greater than 0. X cube, the derivative of x cube is my 3x square, which is always greater than 0. This is a monotonic increasing function. This is monotonic increasing function. Difference of them is a monotonic increasing function. So therefore this is also the bounded variation. Sin x, again the derivative is the increasing function. What is a root x derivative? It's a half of root x. It's always be greater than 0 over this domain. So therefore it is also the monotonic increasing. This is also the monotonic increasing. Sum of the two function is also the monotonic function. Therefore this is also the bounded variation. Remember, this result is only true for the negative and increasing functions. And this I already proved that this is a bounded variation. This is the bounded variation. Sum of the two bounded variation is also the bounded variation. Second is, if f is a bounded variation, then you can easily write as a difference of the two monotonic. That's if and only. That's a converse part is true. If you prove that the function is a bounded variation over the interval a comma b and c is any point, then converse is also true. That means if and only if. The simple example, if I say f is my sin x and domain is my 0 comma pi. So clearly says if I graph them here, clear, this is my pi, this is my pi over 2 and this is my pi. Fine. So once I take from 0 to, if I write here as a sin x over the domain 0 to pi, then your graph will be look like here. Fine. This is my pi by 2. Now clearly says over this interval the function is increasing, over this function is my decreasing. Fine. Also this function is my bounded, because this is my sin x is a bounded function. This is my bounded function. So this is my monotonic increasing, this is my monotonic decreasing. Bounded plus monotonic, this implies my bounded variation. So this over this interval is my 0 to pi by 2 is my bounded variation. Pi by 2 to pi is my bounded variation. So this implies over the complete domain 0 to pi is my bounded variation. Another one, if you prove that f is my bounded variation, then f is my Riemann integrable. Fine. But remember, converse is not true. If f is my Riemann integrable, it may not be a bounded variation. Need not always. Fine. Need not always. But you can clearly say the converse is if the function is my not Riemann integrable, then it implies function is my not bounded variation. If f is my bounded variation, then the discontinuities is always with the countable points. Look at this one. Look at that. The function is my bounded. This is my bounded. Fine. Now we can check about that. This function is bounded, but how many discontinuities points are there? This function is not continuous for all those x. Fine. So what is the meaning of that? And r is my uncountable. So what does it mean? This function, is this a Riemann integrable? This function is not Riemann integrable. So for more detail about the Riemann integrable, how you can check, I recommended you can watch my last lecture PYQ on the Riemann integrations. So this function is not Riemann integrable. It means this function is my not bounded variation. So it means this function is my not bounded variation. The domain is bounded, this function is bounded, but the discontinuities are infinitely many discontinuities, and it is complete R. R is my uncountable. It is not Riemann, so it means it is not bounded variation. The function is continuous only at x is equal to 0. The function is continuous only at x is equal to 0. It means it has discontinuous for all x which belongs to the R apart from 0, but R is my uncountable. It means it is not Riemann integrable. It is not bounded variation. Look at this one. This function is continuous only at x is equal to 0. Fine. It means the function has a discontinuous collection of all those R minus of 0. So what is the meaning of that? This is uncountable. it is not Riemann integrable, hence it is not bounded variation. So these are same of this, so none of them is my bounded variation. The last point is, if f and g are my bounded variation, then the composition of them need not be a bounded variation. If you want to prove them is a bounded variation, make sure the first g is my bounded variation and this f must satisfy my Lipschitz condition, that is the derivative of this should be less than k. For examples, like here, firstly we can check about this is not a composition, but R, what is that R? This R is my unbounded because it consists of minus infinity to plus infinity. If the domain is unbounded, the function is not bounded variation. This is a bounded, sin x over this domain is my bounded, it is also monotonic. So bounded plus monotonic, this implies it is a bounded variation. This is a bounded, over this domain it is a bounded, plus it is a monotonic. So this is also the bounded variation. Look at this one, the domain is my bounded, but whenever tan pi by 2 it goes to the infinity at pi by 2. What is the meaning of that? This is unbounded. Once the function is unbounded, it means it is my not bounded variation. Look at this one, this is my bounded, over this 0 to pi by 4 the limit is my finite, fine, it means this is a bounded, also is a monotonic because if you take the derivative it is my secant square x, over this domain is a monotonic, it is a bounded variation. Now you can see this is a composition, fine. So what is the composition is, this one we need a bounded variation and this one we need a Lipschitz continuously. So you can see this is my G, clearly says cos of x is my bounded variation over this domain. Why? Because this is my bounded as well as monotonic, hence it is a bounded variation. Sin x clearly says that derivative of this sin x is less than 1, hence this sign satisfies the Lipschitz condition. So this implies it is my bounded variation. Similarly for this, it is a bounded variation. This cos x satisfied my Lipschitz condition. So this is also my bounded variation. Remember, this tips continuous need not implies the bounded variation. Differentiability need not implies the bounded variation. I can simply say, you can see sine 1 by x, fine, clearly says this function is continuous, but it is not bounded variation. This is my non-zero and 0 when x is 0. Clearly why? Because a is my 1, b is my 1, but a is not greater than of the b, so it is not bounded variation. Differentiability need not imply the bounded variation. Same example, you can think about that and so on. The last one is, a function f is said to be the bounded variation if and only if the total variation is my finite. What is the meaning of the total variation? First of all, this is not my bounded variation, this is the bounded variation, fine. How you can find the that's a simple. If you prove that this function is my monotonic increasing, then the bounded variation will be my total variation will be my fb minus fa, otherwise here. If I look at the graph of this is the graph of this, so it is a pi over 2 pi 0. Look at that, on this case it is increasing, on this case it is a decreasing. What is the bounded variation of this? Over this case, firstly of this is increasing, so f of pi by 2 minus f of 0, plus over this case is a decreasing, then f of a minus f of b. So what is the f is there? Sin pi by 2 is a 1, sin 0 is 0, 1 minus 0, 2 is the bounded variation of this. Similarly for this, what is that? Sine of over the domain 0 to 2 pi. How you can do? This is my pi by 2, this is pi, this is 3 pi by 2. This is my increasing, this is decreasing, this is this is decreasing and this is increasing. So you can find the bounded variation over this, you can find the bounded variation over this and this. Similarly for each of the case. Fine. You can see if I write here 0, but this is not a bounded variation. Fine, because pi by 2 is a infinite. So if it is not bounded variation, this is not a finite. But if you look about the tan pi by 4, this is my pi by 4, the value is my 1 and here. Fine. So you can find it's an increasing function over 0 to pi by 4. So you can find the boundary variation is f of pi by 4 minus f of 0. Tan pi by 4 is 1, tan 0 is 0, boundary variation is. Now you can see this is my finite. Fine. So if the VF is my finite, then it's also the bounded variation. So either you can find the total variation, or you can check it by the monotonic, bounded, or any as I discussed previously. Now based on these concepts, I can solve all those CSIR NET and the NBHM examinations in a very simple manner. Which of the following is my bounded? So look at that. Domain is my bounded. If domain is bounded, this is also bounded. Fine. Now if this is bounded, is it a monotonic? You can see 2x plus 1 clearly says this is my monotonic function. Whether it's increasing or decreasing, no worry about that. So it means this is my bounded variation. You can also check about that. Instead of this, I can check about whether it satisfies the Lipschitz condition or not. We can find the derivative 2x plus 1. It exists for all x in my domain. Fine. And if you prove that it's a bounded, what is that? It is my 2x plus 1, which is less than of 2 mod x plus 1. What is the mod of x? Is my less than 3. Fine. So what is the meaning of that? It's f satisfied my Lipschitz condition, so it is my bounded variation. So either you can apply the Lipschitz condition, or you can simply say bounded plus monotonic. Look at this one. This is a bounded. Fine. But whenever x is equal to 1, this value will goes to the infinity. So it is a unbounded. So it means it is not bounded variation. When x is minus pi to plus pi, it is always a bounded. Fine. This is also bounded. Now you need to check whether it's a monotonic or not. Sine or cosine is always the monotonic function over this domain. Yes, it is a bounded variation. It's a bounded because it's an open interval, so it can never be goes to the 0. It is a bounded function, plus it is also a monotonic function, because if you take the derivative, it will be minus x over 1 minus x square, which is a finite number because it's an open interval. So hence this is also the bounded variation. So the right answer is A, C and D are my correct answers. Look at this another one. Okay, now you can see what is the A? 1, B is 1. So A is not greater than B. So F is not bounded variation. This is the correct. G. What is my G? X into Fx. So that is my x square sine 1 over x. So clearly says 2 is greater than of the 1. So therefore it is a bounded variation. So G is a bounded variation. It's a not. B and C are my correct answer. Remember, whatever I have told you the previous tips, with the help of the example, just try to listen it carefully. You can solve it in a fraction of a second. Look at this one. Now you can see it's a difference. Fine. If I consider the 2, there are the two methods. You can prove f and g both are bounded variation, or if you prove f and g both are my monotonically increasing function, then this implies it's a bounded variation. This implies it's a bounded variation. So I will tell you here. Firstly, I can think about here. Okay, firstly I can think about here. When it's said to be the bounded variation, when n is my greater than of 1. So when n is equality, cancel. It is not satisfied. It is not satisfied. It is satisfied. Only D is my right answer. Fine. But anyhow, how you can prove this? I can show you. This is there. But what this one? X raised to power k. It is my bounded function. It's a monotonic function because whenever x is non-zero, this is always bounded. It can never goes to the infinity. Whatever the derivative, it's a bounded. It's a monotonic. So what does that mean? It's a bounded variation. This is the bounded variation when this hold. But this is bounded only when k is my greater than 0 or equal to 0. What will happen if k is my negative? I can choose k is my say minus 1. So it will be 1 over x. Clearly says this will go to the infinity when approaches to there. So it is not a bounded variation. Anyhow, if I look about this side, how you can prove? You can see it's a monotonically increasing function only when n is greater than 1. X raised to power k. What is the derivative of this? Fine. When it will be the increasing function? It will be the increasing function only when k is my positive. If k is my negative, then it is a less than 0. So it means k must be greater than or equal to 0. That's why D is my correct answer of this problem. Look at this another one. Clearly say it's a sine and cosine. So A is my 2, B is my 1. So clearly say 2 is my greater than 1. So yes, F is my bounded variation. F dash. Can you find the derivative of this? 2x cos 1 over x minus sine minus minus plus हो जाएगा plus 1 over x. Why? If I take the derivative of this, it's a minus sine 1 over x into minus 1 over x square. So x square cancel, minus minus plus. Now clearly says it is a 1, it is a 1, it is not greater than, so it is not bounded variation. Moreover, I can express this quantity like of this also. Fine. So clearly says 0 is not greater than 1. This is not bounded variation, this is not bounded variation, F is not bounded variation. Now you have to find this absolute value. What is the F dash? You can see it is less than of 2 mod x, because this value will be less than 1, this will be less than 1. So over this domain, what is the mod of x is less than, so it will be 3. So fourth is there here. So right answers are my A and D are my correct answers. Okay, look at this one. Again you can see okay, first F is a continuous, so yes, it's a bounded function, it's a continuous function, that's fine. It's a 1, A is my 1, B is my 1, so 1 is not greater than 1. So what does it mean? F is a continuous function, but it is not bounded variation. F is a continuous, is a bounded variation, cancel. F is a continuous, fine. F is not a bounded variation, fine. F is not continuous, wrong option. F is a continuous function, that's fine, because whenever x is 1, its answer will be 0. Whenever x is 0, it's a 0. So it's always a continuous function, but not a bounded variation. So the right answers are B and C are my correct answers. Look at this another one. Which of the following condition implies the function is necessarily a bounded variation? Now look at that. F is a monotonic function. Look at that. F is said to be the bounded variation if F is bounded plus monotonic, not only a single bounded. Fine. So what can you say about that? Can you say this is, how you can prove that it's a bounded? Monotonic is given. F is defined on the closed interval. Fine. When the F said to be the bounded, if you prove F is a continuous on the closed interval, then it implies F is bounded, because if F is continuous on the closed interval, then it is a bounded. Is the continuous is given? No. So if F is only monotonic, it is wrong answer. You have to prove it's a bounded as well. So first option is cancelled. If F is continuous and monotonic on this, so since it is a closed interval, so this continuous implies bounded. So bounded plus monotonic, this implies bounded variation. F has a derivative at each x. Again, not true, because we need a derivative should be bounded. It is not always has some value, but we need a bounded derivative. So that's the cancel. What is that? It's a bounded derivative. That's 2, because it satisfied the Lipschitz condition. That means this is a Lipschitz condition. So yes, this is a correct statement. So the B and D are my correct answers. Okay, look at this one. Which of the following statement is it? Clearly says F is my not bounded variation. Why? Because A is my 1, B is my 1. 1 is not greater than 1. So f is a bounded variation, option cancel. F is not bounded variation, f is a bounded variation, option cancel. Now you check whether it's a continuous or not, or Riemann. Okay, it clearly says f is my continuous function. Fine, because what is the limit? X approaches 0 negative is a 0, because it's a bounded function, it's a 0 and here. So it is a continuous function. So f is a continuous, he said not a continuous, cancel out. Now how you can prove that it's a Riemann integrable? So since, remember, the one result is if f is a bounded variation, this implies f is Riemann integrable, but converse need not be true, but we prove it's not Riemann, not bounded, it doesn't imply here. How you can prove that? Look at that. How many point of the discontinuities? How many point of the discontinuities? The function is always a continuous. So if the function is continuous, it implies the function is Riemann integrable. That's I already told you in my previous lecture of the Riemann integration. If the function is continuous, then if the function is continuous on the closed interval, sorry, now you can see it's a closed interval. If the function is continuous on the closed interval, then it's a Riemann integrable. So function is a Riemann integrable, correct? Not a bounded variation is a correct. C is my correct answer. Look at this another one. F is my here. Okay. Can you find, okay, F is Riemann. Firstly, we can check about the Riemann. Okay. Again, a very simple. You can see the two function is given to you, x plus 1. This is my monotonic increasing function. This is my monotonic increasing function over this domain. Also, this function is my bounded over this domain. This function is also my bounded. What does it mean? This function is my bounded variation over the 0, 1. This function is my bounded variation over this 1, 2. What does it implies? It implies it's a bounded variation over this complete domain. Fine. So once it's a bounded variation, it means f is my bounded variation over this domain. If f is my bounded variation, this implies f is my Riemann integrable. Fine. The first answer said does not belongs to this, cancel out. F is a bounded variation, correct option. F is not a bounded variation, wrong option. F is not a bounded variation, wrong option. This is it. And you can see what is that discontinuity. You can clearly say is limit x 1 minus is a 1, and so x is equal to 1 is the only discontinuity point. Fine. Or second method is, since f has discontinuity at x is equal to 1 only. What does it mean? Since the discontinuities are my finite, so once the discontinuities are my finite, it means f is my Riemann integrable. You can also see like this way, but if you know it's a bounded variation implies the Riemann integrable, then you can also prove like this way. So this is the way we can see in our last lecture, but right answer is my C is the correct answer. Okay, now you can see it's a difference between the two. There are the two methods. Firstly, you can prove f and g both are my bounded variation, or you can prove f and g are my monotonic increasing function. Fine, I can prove by both way. X cube is a monotonic function over this domain. It is also the bounded function over this domain. So it means this is my bounded variation. Sin of x is my bounded function over this domain. Sin x is my monotonic function over this domain. It means this is my bounded variation. So if f and g are my bounded variation, then f plus minus g is also my bounded variations. Fine. Or sin x, you can also see the function sin x is satisfied my Lipschitz condition. Fine. So it means it is my sin x is my bounded variation, and it's a monotonic and bounded, so the difference is my bounded variation. So this is a bounded variation. Now another is, if f is my bounded variation, it implies f is my bounded, but converse need not be true. Fine, converse need not be true, as I already gave you several examples, like here 1 minus 1, x is in the q, x is in the q complement. So clearly say this is my bounded. Fine, but it is not Riemann integrable. If it is not Riemann integrable, it means it is not bounded variation. So this the converse need not be true. Anyhow, so it means f is a bounded variation, it implies f is bounded. So it means it's a bounded as well as bounded variation. It's unbounded, it's unbounded, it's a bounded but not bounded variation. It's a wrong option. Fine. If you look about here, clearly says x cube is my monotonic increasing function. Why? Because the derivative is 3x square, which is always greater than 0. Look at the another one, sin x. What is the derivative of this? Derivative of this is a cos x. Cos x is always be greater than 0 over this domain. So what is the meaning of that? It is also increasing function, hence it's a monotonic, it's a monotonically increasing. So the difference of the two monotonic increasing is implies my bounded variation. Remember, it is always a monotonic increasing, not the decreasing. So therefore this f is my bounded variation. It implies it's a bounded. So the A is my right answer of this problem. Look at this another one. Which of the following statement is true for the function here? So clearly says, as I can look about the Riemann integration. So this function has discontinuities at 1 over 2 raised to power p. Fine, because from the upside the limit is my here, lower side is a 0. It also has the discontinuity at this point. So you can say the set of the discontinuity is 2 raised to power p, where p is my 0, 1, 2 and so on. Then clearly says that it has infinitely many discontinuities. Fine, but you can see it's a finite number of the point of discontinuities. So this is cancel out. It has an infinite number of the discontinuities, fine. It has infinite, fine. Once they have infinitely here, now you can check whether it's a countable or not. How you can prove that? I can find the limit point. What is the limit point of this? I can check p approaches infinity, 1 over 2 raised to power p, which is 0. 0 is my finite. Can you conclude what is the meaning of that? Is a finite. What is the meaning of that? This f is my Riemann integrable. Fine. So now, okay, they are not talking about the Riemann integrable. Now once it's a Riemann integrable, you can't say it's a bounded variation. But how you can prove that it's a bounded variation? Again, you can see your function is 1 over 2 raised to power p over this domain. Fine. Now what is the function here? Clearly says this is my constant function. Fine. So every constant function is my continuous function, or you can say every constant function is my bounded plus monotonic. If it's a bounded and monotonic over this domain, what does it mean? It is my bounded variation. So f is my bounded variation. It's not a bounded variation, cancel. It's a bounded variation. B is my correct. So none of this is also cancel out. B is my correct answer of this problem. Okay, look at this another one. For the interval I, BV represents the bounded variation. Which of the following statements are my correct statements? Okay, first option is, if f and g are my bounded variation, then the fg is also belongs to the bounded variation. Fine. Is it true? Okay, as I mentioned you earlier, when the product will be here, if you prove that f and g are my bounded, if f and g are my bounded, then only the product is my bounded variation. So can you say, is it given that f and g are my bounded? No, because he said f and g belongs to the bounded variation. How you can say it's a bounded or not? How you can say? Okay, we will think about here. Look at the next one. Fn is a sequence of the Bn which converges to f pointwise. Okay, one more shortcut tips for you. If Fn converges to the f pointwise, then this f will definitely belong to the bounded variation. If converges pointwise, remember. So he said a sequence converges pointwise, then f belongs to the bounded variation is the simple, that's a simple result about that. If Fn converges to the f pointwise, then f is my bounded variation. If f is a function such that f restriction of the closed interval belongs to this, then f is again the same. There's a restriction of this, so there is nothing about it. There's the same problem of this. Look at the last option. If I quickly rub on this side, okay, function is here, is belongs to this or not. If I write this function like to be here, fine. Now clearly says this function is not monotonically decreasing. Why? Because it's a monotonically decreasing function. Its a derivative is minus 1 by x square, which is a decreasing function. So the difference of them, if this is monotonic increasing, this is monotonic increasing, then only is a bounded variation. So it means it is not a bounded variation. So we can see the first part, if f and g here. So you have to prove f and g product is bounded. If okay, now since this is a bounded variation, what is the meaning of that? F and g are my bounded. Fine. So if f and g are my bounded, so what is the meaning of that? F and g are bounded, so product is also bounded variation. So this is the right answer. I will relook about this C part because this said the restriction. This is the result, that's fine. If Fn converges to the f of the bounded variation, then this f is my pointwise. Then if Fn converges to, if f is a function such that Fn restriction to here over this domain is belongs to my bounded variation, then f is also belongs to the bounded variation. I think that's a correct statement. Okay, I will come back to this later on, but I think this is a correct statement. Okay, look at this another one. Just February 2004, every positive here, which of the following statements are true? Bounded variation, fk, they are not talking about the, so fk is basically here, because k is my here, this is basically a sequence of the function. Fine. Okay, so if they are sequence of the function, I can again use this concept. If it converges pointwise, fine. If I prove that it's a converges pointwise, then this f is my bounded variation. So firstly, it's a sequence of the function. You can see again a sequence of the function. When the sequence of the function converges uniformly, we can firstly find the limit of this as k approaches infinity of this. Fine. So what is the answer of this? So when k approaches, so this part is a constant. Fine. So what is the limit of this when x is equal to greater than? So clearly says when x is equal to 1. So this is a 1 over 4. And whenever x is my 0, so it's a 0. And whenever x lies between 0 and 1, so this portion will goes to the 0, because it's a any number which is less than of 1, 0 point something, power of k is a infinity, so it goes to the 0. So it is my here. Fine. So clearly says that this function existence, so it means this is my pointwise convergent. Fine. But how you can say it's a converging uniformly? We will need, firstly, we clearly says f is not continuous. Fine. If f is not continuous, what is the meaning of that? F is not uniform continuous. Fine, because we know that uniform convergence or uniform continuous implies continuous. So converse is not continuous implies not uniformly convergent. So it means Fn converges uniformly is a wrong state. Fine, first one is correct. Now if f is not continuous, what does it means? It means fk is my not uniformly continuous. If f is not continuous, what does it mean? It is not Riemann integrable. If f is not Riemann integrable, it implies it is not bounded variation. So for each k, fk is a function of the bounded variation is the wrong state. Fine, a very simple concept. Now look at this one. For every k, this number should be finite. For every k, so I can choose any k. Of simplest one is I can choose k is 1. So what is my f of k? It is x over 1 plus x whole square. Now can you find the integration of this function? I can simply add plus 1 and minus 1. Fine. So what is that? It is integration of 1 plus x minus 1 over 1 plus x square. So this integration is log of 1 plus x, and this integration is 1 over 1 plus x over the domain 0 to infinity. Now clearly says when you put infinity, this value will goes to the infinity. So which is not less than, that means is it existence? It does not exist for k is equal to 1, but he said for every k. So this option is also cancelled. Only correct option left is my C is the right answer. But how you can prove that C is the right answer or not, we will see, because the sequence is not convergent uniformly. Fine. So we can't say this function is nothing but limit of this. We can't say because it is not convergent uniformly. But how you can say that? Very simple. I can integrate this function x raised to power k over 1. Fine. Now what is the k? K goes to the infinity. So what is the means? If I choose k is my 1, then it is my x over 1 plus x whole square. If I choose 2, then it's x square and so on. So what will happen? Very simple. I can discretize this part. I can discretize this part is, I can say coefficient is a over 1 plus x, then b over 1 plus x square, because if I choose k is my greater than 2, then the degree of greater than or equal to 2, then the degree of numerator is more than of this. How you integrate? Like x4 over, how you integrate them? You have to firstly divide them. Fine. You have to divide this. So I can see here. So after dividing, say c x of k minus 2 plus d of x k minus 3 and so on. Now you can integrate this. You can integrate each term over the 0, 1. So a and b are the real numbers. 1 plus x minus b over 1 plus x. How you integrate this? It is c over k minus 1 plus d x minus 2 over k minus 2 and so on, whenever 0 to 1. So whenever you substitute 0 to 1 and then take limit k approaches infinity, you can see this part will goes to the 0, because this number is my 1 is a finite. This part will goes to the 0 and so on. This value is my finite. This value is my finite because 1 and 0 is a finite. So whole number is my finite. So therefore this limit is existence is the right answer. Look at this another one. Which of the following functions is of the bounded variation? Very simple. You can see what does it means. I can return the first function fx over x minus y is less than 3. What does it means? F dash of this is less than 3. What does it mean? It means f satisfied my Lipschitz condition. If f satisfied my Lipschitz condition, it means it is my bounded variation. So yes, it's a correct. If somebody asks you f is a bounded variation, you can also say f is my Riemann integrable as well, but they are not asking you. But if somebody asks you, you can check also. If for some non-negative Riemann integrable on the closed interval here, again what you can do, you can simply take the derivative. It is my g, and since g is my Riemann integrable, fine. If g is my Riemann integrable, what does it means? If f is my Riemann integrable, so since g is my Riemann integrable on 0, 1, so what does it means? It is less than k. So therefore f is again satisfied my Lipschitz condition. Therefore f is my bounded variation. You can't directly say if g is my Riemann integrable, it implies is a bounded variation. So this is also correct option. Otherwise, you can also think like this way, because how you can see, because this is the indefinite integral. Fine. So indefinite integral over Riemann integrable function is always Lipschitz condition. Satisfy the Lipschitz condition. If satisfy the Lipschitz condition, it implies it's a bounded variation. It implies it's a here. F is a monotonically decreasing. Only decreasing is not satisfied. We need a bounded also. How you can prove that it's a bounded? Because it is given that F. How you can prove it's a bounded variation also? Is it true? F is a monotonically decreasing. You need to bound it. Okay. F is a bounded. Is a monotonic decreasing. Okay. F is a function defined on this over this, nothing is given to you, is a monotonic. Fine. If since it is defined on the closed interval, so it's a bounded because it's continuous. No, it's a monotonically decreasing. If it's a monotonically decreasing, then there are two cases: either they have the finite number of the discontinuities, or they have the jump discontinuities. Okay, yes, it's a finite or jump discontinuities. So which is a countable? If it is a countable, then it is a bounded variation. Yes, this is also the correct option. Look at this another one. F is a mapping from this is said to bounded variation. Okay, this is a definition. If F is a closed interval a comma b is my monotonic, then it's a bounded variation. That's the same thing. It's defined on the closed interval, so it's a continuous as well as bounded. So bounded plus monotonic is correct option. F is a C1. What is that? The C1 is continuously differentiable function. What does it mean? If F is a continuously differentiable function, means F dash exists on closed interval a comma b. What does it means? F dash is my continuous. If F dash is continuous, it means F satisfy the Lipschitz condition. So it means it's a Lipschitz condition. Hence, it is of bounded variation. If F and G are my bounded variation, the sum is also the bounded variation. That's also the correct statement. Moreover, sum and the difference will always be the bounded variation. Look at this another one. A is a finite interval. F is given to be my bounded plus Riemann integral. It is already given to you. Define the function capital F over this domain. Which of the following statement is there? Now, what is that? I think that's a very simple. Why? Because again, this is my indefinite integral. Fine. This is my indefinite integral plus this F is my Riemann integrable. What does it mean? This means this is satisfied my Lipschitz condition. If this satisfied my Lipschitz condition, what does it mean? Capital F satisfied my Lipschitz condition. It means F is my bounded variation. If F is bounded variation, it means F is my bounded. Also, F is Riemann integral. So this is my bounded variation, correct option. Another way, you can find the derivative of this. What is F dash? F dash is nothing but F of x. And if you take this, what is that? This is of this. And what is the F is given to you? Bounded. So it means it is less than or equal to something k. That means capital F satisfied my Lipschitz condition. So it means it is my bounded variation. Fine. Now, if it is a bounded variation, you can simply say it is moreover, you can easily say it is a uniform continuous function, and F is a differentiable. We already proved that because it's a Riemann integrable. So all are my correct options for this particular example. So you can see a very simple approach. You can find the solution of this one. Another, I can recall that quickly. What is the simplest way you can see? If F is my bounded variation, this implies it is my bounded. But remember students, if it is a bounded, it doesn't implies it's a bounded variation. Similarly, if f is a bounded variation, it implies it is my monotonic here, but only the monotonic does not implies it is my bounded variation. You need a bounded plus monotonic, then it is a bounded variation. If f satisfied any of the Lipschitz condition, then it's a bounded variation, but bounded variation does not implies it satisfies the Lipschitz here. If the function is my continuous, it doesn't implies my bounded variation. If f is my differentiable, it doesn't implies it is my bounded variation. If f is my uniform continuous, it doesn't implies my bounded variation. If f is my bounded variation, this implies it is my Riemann integrable, but again converse need not be true. So I hope based on these simple shortcut tricks, you can solve any of the boundary variation problem in a very simple manner. I hope you can simply like, share and comment on my video. Next video we will see on the improper integrals. Till then, you can simply share my videos with your friend. Best of luck, students. Happy learning always.